Okay, so a point that came up in the during the break. So let me just make that point here also. When these sizes become macroscopic, okay, so when you get something of the order of millimeters, etc., then this quantities A and B become so large that the contributions from incremental increases in N1 and N2 approach a continuum. Okay? So if A and B are very, very large, then changing N1 and N2 make very little changes at a time so that it approaches a continuum. So in that case, you can treat, okay, the motion in these, okay, extended directions as if the particle is a free particle, right? Then in that case, these sine, okay, n pi over a x, for example, may be approximated by e to the I, okay, some kx, where k is this n pi over a, and it may be approximated as a continuum. Okay, so that's something to keep in mind. We'll consider those things in more detail later on. Okay. Okay, so that's actually all I want to say about the rectangular geometry. It is useful because you can obtain results pretty quickly, and yes.
Professor, for these shapes, from the back they have also high voltage, right? Because we should have we should have a closed.
Yes, okay. So again, the arguments that I gave here for lower potential at places where the particle we expect to move and higher potentials at other places, obviously you must have the same structure over here. Okay, so you need to have, okay, gallium arsenide here, and in the outside region you have what's known as gallium aluminum arsenide, except that one is X and one is 1 minus X or something. Okay, so you dope the system with aluminum so that that raises the effective potential in which the particle is moving in. So you are going to get confinement. Okay, so the particle is confined, okay, squeezed in into those regions. Okay, yes.
I have a question about the threefold degeneracy.
Yeah.
So, for example, for the E222 state, there is only one state, there is no degeneracy, right?
E222, well, okay, you have to ask a number theorist whether you have other possibilities of n1 squared plus n2 squared plus n3 squared equal to what? 12? Yeah, seems reasonable.
But
113 is what? 11, so that doesn't hold. Okay, I guess, yes.
so what, I mean, what changes, like what's the meaning of the degeneracy?
Okay, what does it mean to have a degenerate state? For a single particle, if I have a single particle inside this box, okay, it can go to any one of these states. Okay, so when you write down the possible states that a particle can be in, it can be in, okay, this E11 or E211 or E222, etc., in any one of those states. And so what you have is, okay, even then you have to be careful when making certain calculations such as transition probabilities from one state to another. The problem becomes more interesting when you have more than one particle in it. Okay, so if you have more than one particle in the system and you want to put the particles into the lowest possible energy states, you see, if I have a single particle, then it's obvious. It has to go to E11, E111. If I have a second particle, I want to put it into the lowest possible energy state. It turns out that I can still put it into E111 because we'll see that we can put up to 2 particles into a state depending on the type of the particle. Now, if I have a third particle and I want to put it in there, it really depends on what type of particle that I have. If it is the same type of particle and an electron, a type of particle known as fermion, we'll look at those things possibly by the end of, not next week, but the week after that. Okay, so if it's a fermion, I can put only 2 particles into an energy state. The third one must go to a different state. Okay, so it can go, the third particle can go to any one of those degenerate states. So it increases the number of options you have. If it's a type of particle known as the boson, you can put all of them down in E11. Okay, so those are very nice. Okay, social particles. You can put as many of them as you like into the same energy state, and they like it. Okay, the fermions, on the other hand, they can be only 2 per state, and even that, when you put them in the same state, they then have to have their spins in different states. Okay, so fermions want to be different. Okay, from one another, so they cannot be. So the energy states and their degeneracies are such things are important when you go to more than one particle states, like a material, for example. Then it will be very important.
So for fermions, there can be 6 particles on the energy state that has.
Yes, for fermions, you can put 6 particles into E121 energy state, but you can put only 2 to the E222 state. Okay? Yes.
What are the applications of quantum?
What are they?
Application of
Quantum?
dots.
Quantum dots? Okay. Well, even now you have these television systems which advertise themselves as quantum dot stuff. Okay, so generally what you do is you adjust these energy states, okay, energy differences, to a certain energy which corresponds to a certain color of light. Okay, so if you want some commercial application, you can just have these things so that they generate light only at a certain frequency or certain wavelength. So you can make these light emitting devices such as lasers, television screens, etc., all that type of stuff, which will give you certain colors under certain conditions. Okay, so you can adjust them to generate patterns and such things. So that's probably the most common application. Okay, their interaction with light is the application. Otherwise, of course, you can do various experiments depending on the lifetime of these states. For example, if you can keep the particle here at a higher energy state for sufficient period of time without having it decay, well, you can say this is state 1, quantum state 1, and that's quantum state 0. So if you have just a 2-level system, it becomes what's known as a qubit instead of ordinary computer bit. Now you have a quantum bit, okay, which stores 1 bit of information. So you can play around with those things, and okay, it's now science sounds like half science fiction, but you have these options of creating quantum computers and things of that sort, okay, with these things. So depending on how much you can control these states, okay, you can use them in very different types of applications. Okay. By the way, this year's Nobel Prize in Chemistry went to the quantum dot people, and their quantum dot is actually a better quantum dot than I have drawn here because it's a spherical object. Okay, so they have made these spherical objects in which they can trap a particle in. Okay, and so the energy levels will be different because now you have to solve the equation in spherical coordinates, which we are going to do next. But then again, you get these energy levels and just play around with them. Okay, so we can just check the internet for chemistry Nobel Prize this year. Yeah.
When we are creating this formulation, we created the Schrödinger equation for any kind of particle,
Mhm.
right? In this
Yes.
box.
Yes.
Doesn't matter what's the particle or what's the thing inside.
Yes. It's this is always valid for any type of particle, but if you want to control it by using semiconductor technology, electrons are the easiest ones. Okay, if you want to do the same thing with protons, well, okay, probably could be done, but I don't even know how to approach it. Okay, so you can obviously trap particles, but if you want to trap them into small places, you have to use the electromagnetic interaction, and that's usually a charged particle. Okay. Other questions? All right. So let's now go to the spherical coordinates. Okay, so I already have the equation here. Time-independent Schrödinger equation. Except that now I have to write it in spherical coordinates. And since I'm not one of those mortals who know the del squared operator in spherical coordinates, I have to check my notes. All right, so I have minus h bar squared over 2m, okay, del squared operator. Okay, and del squared operator is 1 over r squared del r. So let me put the spherical coordinates here. Okay. R squared del r. Okay. Plus 1 over r squared sine squared theta. Sine theta, sorry. Del theta. Okay. Sine theta del theta. Okay, and plus 1 over r squared sine squared theta del squared del phi squared. Okay, so that is now my del squared operator operating on this u, which is now going to be a function of r and theta and phi. Okay, so I have only written the first term yet. Plus v over r times u is equal to EU. All right, so that's the equation. And if you look, it looks scary. Yes, I guess you should be scared of it. Okay, it produces some interesting special functions and everything. But we'll go step by step. And in fact, what we'll do is we'll use the operator technique so that we will not need those special functions, actually explicit form of the special functions. Okay, so you see what I'm going to do is I'm again going to use separation of variables. Okay, so I'm going to just separate this u into pieces. So I'm going to have this r of r multiplied by theta of theta, phi of phi. Okay, so that will be the form that I'm going to use. In fact, this theta of theta and phi of phi is usually just combined into a single function of theta and phi. The angular part is treated separately. Okay, so what I will do is this piece here, okay, the angular part, I am going to give it a name so that I don't have to write this long equation again and again. So let me just rewrite the equation doing that. Minus h bar squared over 2m, okay, 1 over r squared del r squared del r. Okay, then I have this theta and phi part. That theta and phi part I'm going to write down as plus, okay, minus in fact. Minus, okay, some operator which contains thetas and phis in it, which is this thing here. But I want to actually separate out the r squared and also the h bars, put an h bar squared here. Okay, so it's just my definition of that thing. Okay, so this whole thing I'm going to write as that. Okay, so it has some r squared dependence, so I'm going to write that out explicitly, and then that's some operator divided by that. Okay, so just u plus v times r. Okay, so you see, let me put a vector sign here. So this is, in general, the potential can be a function of position, okay, which may depend on r, theta, and phi. By the way, I have not drawn this, but I'm assuming that all of you know what we mean by r, theta, and phi. So if I have x, y, and z coordinates, okay, and I'm pointing at some point, some vector r, so I can just look at the, specify this vector either by x, y, z coordinates, or I can just, okay, look at these angles, theta, phi, and the distance r from the center, okay? Now, over here, I'm not going to put in the vector sign, okay? So this is going to be EU. So what I'm doing here is I'm assuming that, okay, V is spherically symmetric. So what does that mean? It depends, the potential depends only on the distance from the origin. Okay, it doesn't depend on theta or phi. It depends only on the magnitude of this r. So no matter where I am on this sphere, which has the same value of radius, the potential is the same. Okay, so the potential has spherically symmetric form. Okay, this is also called a central potential. So it's a central potential because it depends on the distance to the center. Right, so this terminology you may have seen in classical mechanics also, right? Okay, so I have something like this. So what did I really do here? Let me just put this, okay, factor inside, minus h bar squared over 2m, 1 over r squared del r squared del r. Okay? And then I have this next term, which is going to be plus this L squared operator, theta of phi. Okay, theta and phi. And then when I do this, I'm going to get here a h bars are going to cancel, and I get 2m r squared u plus vu equals eu. Okay, so that's my Schrödinger equation. Now, you see when you look at this term, this is just going to be a, okay, semi-quantitative, semi-qualitative argument. You see, this term here involves derivative with respect to r. So this whole piece, okay, the del squared part, remember, is the kinetic energy. So these derivatives with respect to r correspond to something like radial motion, the motion of the particle, okay, as it moves away from or into the center, okay, as r changes. These things are related to angular change. Now, in angular change, if I had, for example, okay, so let's just do a little bit of classical mechanics here, right? If I have something rotating around a center, okay, so it is, suppose I have an object with mass m and moving with velocity v, right, at some radius r. What is its kinetic energy? Well, let's write down the angular momentum. L is equal to mv times r, right? Now, L squared is m squared v squared r squared. What about L squared over 2m r squared? Well, it's 1 over 2 m v squared. Okay, you see L squared over 2m r squared, when L is the angular momentum, gives you the kinetic energy of the particle due to its rotation. Okay, so in fact, this will turn out that this L squared object, this L squared thing that I have written here, which is an operator in terms of theta and phi, is the angular momentum operator. Okay, so this is not a simple transformation, but the details are in your textbook. Okay, so a few pages of algebra. You can show that this is equal to the angular momentum. Let me just give you a taste of what you have to do just to see. Okay, let's look at the phi derivative. Phi derivative is usually nice and easy. Okay, so I have these definition of the spherical coordinate variables. So I'll just redraw this figure here. I have the x, y, and z, and that's my vector r. That's the angle phi. It's called the azimuthal angle. And theta is the polar angle. Okay? So I have something like this. How are these things related to one another? For example, given r, theta, and phi, how can I find x, y, and z? Z is the easiest, right? If I know r and theta, I know what z is. What is z? Okay, z is r cosine theta. What about x? Okay, r sine theta, puts it on the xy plane, then I have a cosine phi, and y is r sine theta sine phi. Okay, so that's how r, theta, phi are related to x, y, and z. Now, suppose I have a function of x, y, and z, but I want to find the phi derivative of it. Okay, so I have a function of x, y, and z, but I have to find the phi derivative of it. Now, phi is hidden inside all of those variables. Okay, so how do I do it? Well, just del.
Over del x times del x over del phi plus del f over del
Okay,
phi.
well, if you say that faster than I can write, then I can, of course, del x, del, okay, let's
Phi.
go, okay, phi, plus,
Del f over del y over del f dot dot dot.
okay, well, that part I have to write down, plus del f, del z, del z, del phi. Okay, so let's just look at that. So del f, del x times del x, del phi, which is going to be minus r sine theta sine phi plus del f del y, okay, r sine theta cosine phi, and finally 0. Very good. So, but now this thing you see is what? R sine theta sine phi is y, so this is going to be minus y del f del x plus this thing is x, x del f del y. Now, okay, I don't know if you can identify this, but this is actually related to angular momentum in the z direction. Okay, how do I find the angular momentum in the z direction? Well, it's just r cross p, but I take the z component, right? So it's going to be, let's write down the operators. Well, let's just first do the algebra. So it's going to be x times py minus y times px, right? That's the z component of r cross p. Let's put in the operators using h bar over I. So it's going to be h bar over I, x del y minus y del x. But you see that's exactly what we have here, right? We don't have the h bar over I, but this is exactly the same. So if I now put in h bar over I, del phi is equal to, okay, Lz. So you see these things, okay, without the h bars can be related to these derivatives. So there's you see there's an Lz hiding here. Okay, Lz squared, in fact, hidden there. It has a prefactor and everything, but that's just to give you a sense of what is needed. The Ly and Lx are more complicated cases, and because they are not simply related to simple rotation around an axis. Okay, so you are going to get more complicated terms, but at this point, trust me, in fact, more than me, trust Griffiths, that, okay, that's just going to turn out that way. Okay, so that's what we have, okay, in terms of these things. Now, let's do our separation of variable stuff. Okay, so the separation of variable stuff, let's go over here. How much time do I have? Okay. Okay, so now I'm going to put in a form for u, okay, which will be in the form of r of r and y of theta and phi. Okay, so I'll separate the radial and the angular coordinates. So before I do that, let me multiply everything by r squared and then put this in. So maybe I can do them both in the same step. Minus h bar squared over 2m. Okay, I'll multiply everything by r squared. So it's going to be d dr. Okay, ordinary derivative because now it's going to operate only on r. R dr dr. Okay, times y because y is a function of theta and phi only. So it just comes out. Then I have the other term. Now that term is plus L squared over 2m, right? And then, okay, this is operating on, so this is a function of theta and phi, remember, it's an operator. And it operates on y, theta, and phi. And I'm going to get here r again. Then plus r squared v times r times y, okay, is equal to e times r times y. Okay, so I now divide everything by ry. Yes.
Don't we need to multiply with r squared as well?
Yes, thank you. Okay, so I divide by r times y, so I get minus h bar squared over 2m d dr r dr dr. Okay, let me put this r squared term over here also. R squared v, okay. Well, I'm dividing by r times y, so I need to have this thing divided by r, right? So I'll get plus v, and that's it, vr, right? I'm dividing by r times y, and r squared. Plus, okay, maybe I'll just put this over here also, minus e r squared plus L squared theta phi over 2m, right, operating on y divided by y is equal to 0. So I have an equation like this. You see on the left-hand side I have just a function of r, and over here I have a function of theta and phi. Okay, so these things now are going to be constants. Okay, I have to be careful because the way I have done this, I have kept the 2m here. Maybe I should multiply by 2m also. Sorry, I'm being somewhat sloppy here, but I'll just multiply everything by 2m so that I get something unitless. Well, not unitless. Okay, so multiplying this by 2m just cancels that. Okay, so I have something like that. Okay, so now we are going to have to set these things equal to certain constants. And those constants, as it turns out, okay, this one is called L plus 1 times h bar squared. okay, because L is going to have, being angular momentum, will have units of h bar. So to make it equal to a constant, that's what I have to do. So obviously then this whole thing will depend on L minus L plus 1 h bar squared. Okay, so that will be the type of the solution. So these things are going to give us what are known as spherical harmonics, y Lm of theta and phi. Okay, these things are called spherical harmonics. Okay, these are functions that you ordinarily see in mathematical physics courses. I am assuming that practically all of you are exposed to what spherical harmonics are, right? You don't have to remember them, but do you know the name?
Yeah.
Okay, so you know as much as I do, okay? So whenever I need such things, I have to look it up in a table or something, but these are some special functions that go out like that. Okay, so what I'm going to do here now is put 3 dots, dot, 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 which means we are going to return to this problem later. Okay, so we'll return to this problem later, but we want to study this angular momentum part. Okay, we will not need YLMs just yet. Okay, but we'll now move on to angular momentum. So if you are following me from the book, this is now a big jump. Okay, we have jumped over solution to this equation, lots of algebra, the hydrogen atom, etc., etc. We just jump all over those things, and we'll just discuss the angular momentum because it can be done much more easily, okay, much less algebra, and much more intuitively. And then once we just do everything that we can do with the angular momentum, we'll return back and look at the radial equation. Okay, so this piece here is called the radial equation. And this piece here, no surprise, angular equation. Okay, so we'll not even look at the angular equation, but we'll just look at the problem of the angular momentum. Okay, thank you. Okay, now one thing that you can see immediately by looking at this equation is you can notice that okay, so let me just say that. Notice that, okay, if I take the whole Hamiltonian, the whole H, and look at its commutator with L squared, the operator L squared, what do I get?
I think 0.
Okay, you think correctly. Now let's see why you think that way.
Because Hamiltonian composes as a radial and angular term, angular square clearly commutes with the angular term and also radial term.
Yes, okay, so L squared is an operator which contains thetas and phi derivatives only. And obviously it commutes with itself, right? L squared will commute with itself. But L squared will also commute with all this stuff because there's no theta dependence in that part, okay? So that means I'm going to get 0. So that means, okay, remember our terminology, L squared is a constant of the motion. Okay, so a very less fancy way of saying that is L squared is conserved. So angular momentum is conserved. Actually, the magnitude of angular momentum is conserved. Okay, you'll see that there is a more general conservation law, but the angular momentum is conserved if this commutes with that. And in order to have this commuting with itself, you see, we said L squared will commute with this radial part, which contains the potential. Okay, so if potential contained an angle, if the potential was not central, then I could not say that, right? Then it would not commute. So if I have a central potential, a potential that does not depend on the angle, that means angular momentum will be conserved. Now, is that sound familiar to you from classical mechanics, right? Yes.
So I couldn't understand why this commutation is equal to zero. I couldn't understand.
Okay, so I am just trying to find the commutation relation of this H, which contains terms like del, del R, okay, whatever, things which have derivatives with respect to R, and also a term which contains L squared. Okay, so now obviously L squared commutes with itself. Okay, okay. The other part, this contains only derivatives with respect to R, and there's no R in L squared, and there's no theta in that. Okay, so they will commute. So there is no way this operates on L squared. Okay, so L squared is just like a constant. It will just move to the left, which means that they commute. Okay. So if this had some R in it, for example, then of course I couldn't say that. Then this would differentiate that R, and it would be important which way I do that operation.
By the way, how in the Hermitian operator, I understand but how do we know that the term is, first term is dependent on the R squares and the plus there is L square. Maybe in first part there is, in the second part, maybe there is also R dependency.
No, but we know what these things look like, okay? They are over here. Okay, this is L squared is, okay, this thing without the R squared. It contains only thetas and phis.
Okay.
Okay, it contains only thetas and phis. And similarly, the R part is something like this, which contains no thetas and phis. Okay, okay. So with our choice of the potential, which is spherically symmetric, we know that this L squared, the eigenvalues are eigenvectors will be also eigenvectors of the whole Hamiltonian. Okay, so let's start. I have 5 minutes, and with your help, I can do the first part. Okay, so let's look at the commutation relations of the angular momentum operators. Okay, so I already looked at LZ as an example, but let's just write down all these operators. Lx is going to be y pz minus z py, right? Okay, so Ly is going to be z px minus x pz. So you see I'm going cyclically x, y, z, and then reversing the order with a minus sign. And Lz is equal to x py minus y px. Okay, now let's look at one of these things. Let me start a fresh board. All right, so let's see what commutator of Lx with Ly is. So it's going to be the commutator of ypz minus zpy with, please check my algebra, zpx minus xpz. Okay, we have seen the distributivity, etc., of all of these operators. So this will just result in 4 commutators, right? So, okay, first with first, ypz with zpx. Okay, and then minus ypz with xpz. Then I have this minus zpy with zpx. And finally plus zpy with xpz. Okay? Now, I have to look at for things that do not commute. Now, obviously, things like y and z are different directions. They commute with one another. Similarly, pz and px commute with one another. The only things that do not commute are things like, okay, let's see, x and px, remember, is I h bar, but I must have the same thing with all of these things. Y with py is I h bar. Z with pz is I h bar, right? So coordinates in a certain direction and derivatives do not commute. So, okay, so I have this stuff, for example, pz and z, which will give me something finite. Over here, everything commutes. X, y, pz commutes with itself, so this is 0. Over here, I have z and z, obviously it commutes with itself. Py and px are in different directions, so that's 0. So I only have, okay, z and pz term here and that over here. So I'm going to get, okay, things that are not involved in commutation, I can just take them out. Y times px and commutator of pz with z. Over there, things that are not involved in the commutation are py and x, so they commute px, py, and then I have what? Z and pz. Okay, so this is in the wrong order, pzz, so it's going to be minus I h bar. This is going to be I h bar. So I end up with I h bar z xpy minus ypx. So which one is this? Xpy minus ypx? LZ, right. Okay, so there's an I h bar in front and LZ. Okay, so that's what I found. So let me just make a small table here. Lx commutator with Ly is going to be I h bar Lz. Now, the others I don't really have to calculate because these are 3 orthogonal directions, right? And they are related to one another just by just a simple rotation. So if x goes to y, y goes to z, z goes to x, I should get the same thing, okay? Space is isotropic. There's no reason why x, y, and z should behave in another way than, okay, Ly and Lz. So as long as I keep the order x, y, z, Ly Lz is equal to what?
I H bar Ly.
Okay, I H bar, next thing, Lx. So the next one out is Lz with Lx is I H bar Ly. Now it turns out that these three commutation relations, just this stuff is sufficient to derive all properties of the angular momentum operator. Okay, so it's just like we had these A plus, A minus operators in the harmonic oscillator, and we derived all the energy states and everything, okay, using those operators. In this case, we are going to use these three commutation relations. We'll generate some other operators as well. But at the end, we are going to get, okay, again, similar relations. Okay, so I'll let you go. We meet on Monday, and on Monday, you should come with questions so that we can solve the questions. If there are no questions, I'll go on with angular momentum. So if you like angular momentum so much, you don't have to ask me questions, and we'll go on.